Okay, so hi everybody. We're going to go over our test 3 review. Okay, I've got the problems here on the left. You can see number 5, we've got a list of things to do. So as you can see, well, I mean, I don't need to rewrite it, right? So the magnitude, if you look at A, magnitude of U, would just be this, I mean, the formula is the square root of U dot with U. And of course, that'll come out to be the square root of 1 square plus negative 2 square plus 0 square plus 1 square. Like that. And if you go through that, obviously, not a big deal, but that's the square root of 6. Okay. So on B, they want the norm or the magnitude of V. So as before, that would be the square root of V dot V. Okay, so this time we'll do 1 square plus 1 square plus negative 1 square plus 0 square. So that looks like the square root of 3. Okay, now on C, we have to do U dot V. Okay, so we'll do 1 times 1 plus negative 2 times 1 plus 0 times negative 1 plus 1 times 0. So it looks like that comes out as a negative 1. And then D. Here we have to do the distance from U to V. And you think of that as the distance from the tip of U to the tip of V. It's basically the two positions. So that's the norm of U minus V. So that U minus V connects the tip of U to the tip of V. Really the tip of V to the tip of U, I think. So this would be the norm of the difference of the two vectors, which is going to be 0, negative 3. Oops. 1, 1. Pardon me. So we'll do the square root of 0 square plus negative 3 square plus 1 square plus 1 square. So that looks like the square root of 11. Okay, so that is problem 5. All right, let's do number 9. Okay, so you can see V here. We have to find a unit vector that points in the direction of V. That's easy. So we have to take the norm or the magnitude of V, which is the square root of V dotted with itself. So it's V dotted with V. So here we're going to get a 5 square plus a 3 square plus a negative 2 squared like that. And so That's 25, 34, 38, square root of 38. Like that. And then the unit vector, I'll just call it u for the unit vector. And this has to be v over its magnitude. Okay, so obviously we'll do -2, hang on, 5, 3, -2, and then divide that by the square root of 38. And you can run that through, and obviously there's multiple stages of simplification. I'll just do this much, and then I'll let you guys worry about the rest. Okay, any questions? I guess there's no point in asking if you have questions. Hopefully that makes sense. Sorry. No, there we go. All right, so then next I have number 19. So here I'm supposed to do the angle between the two vectors. So just remind you, cos theta is u dot v over the magnitude of u dot times the magnitude of v. Okay, so we'll go ahead and do u dot v real quick here. U dot v on 19 will be 10 times -2 minus 5 times 1, and then plus 15 times -3. And what do you get there? -25. Hang on. -25 minus 45. I think I get -70. I'm going to double check this. Yeah, so -70, I think. And then magnitude of u. I think I want to factor out a 5 from that. So I'm going to factor out 5 times the magnitude of 2, -1, 3. Like that. Okay, so that'll be 5 square root, oops, of 2 square plus -1 square plus 3 square. Like that. So let's see, that's 4, 5 plus 9 is 14. So I think that's 5 square roots of 14. Like that. And the magnitude of v, and v is -2, 1, -3. That sounds very familiar. So we'll get the same, almost the same as the last one without the 5. So here we'll get the square root of the -2 squared plus 1 squared plus 3, -3 squared. So it's 4, 5, and 9 is square root of 14, like that. And so when we do cos theta, we see we're going to get a negative 70 over 5 root 14 times root 14. And then 5 times 14 is 70. So in the end, you get negative 70 over 70. So this is -1. Okay, and now it's pretty easy to see that theta will be pi. And that's our answer. Okay, any questions about that one? Let me know. Okay, so there's 19. Let's see, now we got to do 29. So let's give this one a go. So F, I'll just call it F. F is X. G is 1 over X squared plus 1. Okay. Now, the inner product of F with G will be the integral from -1 to 1, because that's the interval over which these are defined, of X times X squared, 1 over X squared plus 1. And I can make this real easy for you. You can do your work, but you might notice that this is an odd function over a symmetric interval. So let's make the note. This is going to be 0. We have a symmetric interval, meaning it's centered at 0. Yeah. And we have an odd function. Okay. Anytime you integrate an odd function over a symmetric interval, you get 0. So you don't have to do any more than make it clear to me that you've checked that. Now, since we got 0, this tells us that F and G are orthogonal. And when I say they are orthogonal, I mean they are orthogonal on the interval from -1 to 1. They may not be orthogonal on other intervals. Okay, so the answer to B up here is that the two vectors are orthogonal. Now for the Cauchy-Schwarz inequality, this is actually true trivially, because the inner product is definitely less than the magnitude of F times the magnitude of G. But I'll just do this real quick. So the magnitude of F is just defined as the square root of the inner product of F with itself, which would be the integral, well, the square root of the integral from -1 to 1 of F times F. So I'll just put that in, F times F, that'll be dx. Okay, so in the end, you're doing the square root of the integral from -1 to 1 of x squared. Okay. So that's the square root of 1/3 x to the third from -1 to 1. So I think that's going to be 2/3, right? So it's the square root of 2/3. And I guess we could call that the square root of 6 over 3, right? That's the norm of the magnitude of f. I'm just going to paste in the magnitude of g because there's a little bit more work. I had to do a trig substitution to get this. So yeah, I had to do a trig substitution to get that one and didn't like it. It's sort of clear, you know, the Cauchy-Schwarz inequality says that the absolute value of the inner product of f with g has to be less than or equal to the magnitude of f times the magnitude of g, which is not trivial to prove in an abstract concept. See, it's obvious in R2 or R3, but we'll just let that pass for the moment. What we've got here is that the inner product of f and g is 0. Okay, and so this is going to be less than or equal anyway to the magnitude of f times the magnitude of g regardless. And neither one of those is going to be 0, because I just want to remind you the only way the magnitude of a vector is 0 is if the vector itself is 0. So neither one of these is 0, neither f nor g. So this is going to be greater than or equal to 0. It doesn't matter if it's greater than or equal to 0. This is obviously true. Okay, so we actually don't even need to do the integrals for this one, but I did them just in case some of you guys were beating your head against the wall over it. So I didn't want you to inflict too much damage. So there's number 29. Okay, so let's look at number 35. The formula for the projection onto V of U is the inner product of U with V over the inner product of V with V. Those are all scalars times V. If you like the dot product notation, I mean the dot product. Let me put the barbs over these. Okay, so the dot product of U and V over the dot product of V and V. So this is just alternate notation times V. Okay, so U dot V, just for that numerator, looks like 0, -2, and 8. So it's -2 plus 8, which should be 6. And the denominator of V dotted with V, so that'll be 9 plus 4 is 13. Plus 16 is 29. So that doesn't reduce. And then times V, which is the 3, 2, 4. And if you want, oops, where'd it go? If you want, you could distribute that through and just say 18 over 29, 12 over 29, and 24 over 29 is that projection. And that looks good. Okay, so we're on 39. I'll go ahead and we're going to use Gram-Schmidt orthogonalization, and then we'll normalize the vectors, which means to make them unit vectors. Some of these are pretty easy. For instance, the first two are already orthogonal if you look at that dot product. So there's actually gonna, this should go pretty quickly. I'm gonna go ahead and name these V1, V2, and V3. And the Gram-Schmidt process goes something like this. We would let W1 be V1. So that's just going to be 0, 3, 4. Okay. Now W2 is already going to be orthogonal to W1. You can see this. What we're going to do is just take, I'll go through the process. You would take V2 and subtract the inner product of V2 with W1 over the inner product of W1 with itself times W1. Okay. And so that's just the formula. And so you'll see that V2 dot W1 will be 0. So with V2, we're just going to take 1, 0, 0. And then V2 dotted with W1. You can just look at these two being dotted, well, these two being dotted together. You'll get 0 out of that. So the rest of the computation is actually sort of irrelevant. You're going to have a 0 over, this would be W1 dotted with W1, and it doesn't matter what that is. And then we're going to multiply it by W1. Okay, so this is just going to be 1, 0, 0. So there's nothing else really to do with that. It's super easy. Now the last one, W3. So here we're going to take V3, and we have to subtract out the W1 and the W2 components from V3, so that it comes out orthogonal to W1 and W2. All right, so yeah, we'll start with V3. Okay, and we're going to subtract out the W2 component of V3. So that's going to look like the dot product of V3 with W1 over W1 dotted with W1 times W1. So that's the W1 component of V3. And then we have to subtract out the W2 component of V3. So we'll take V3 and dot it with W2. Same computation really, but we're just doing it with W2. Like that. Okay, and then we can just see if how much we can do here. So V3 is the 110. And then V3 dotted with W1, to me, that looks like 0 plus 3 plus 0. So I think it's just 3. Okay. And then W1 dotted with W1. So that's going to be a little messy. So you're going to have 3 squared plus 4 squared. So that's 9 and 16 is 25. Like that. And then times W1. So W1 is 0, 3, 4. Like that. And then the next one, so we have to do now minus V3 dotted with W2. So V3 with W2, you're going to get a 1 plus a 0 plus a 0. So I think it's just 1. And then we have to do over W2 dotted with W2. And again, keep in mind, W2 is just 1, 0, 0. So if you dot it with itself, you get 1. And so that'll be times 1, 0, 0 there. Now, I've mentioned it's a good idea to clear fractions on this, and you can multiply with these by any non-zero scalar. So just to make this a little easier, I'm going to multiply this by 25. Okay. And I may do something else as, multiply by something else later if it helps. So anyway, we're going to have a 25, 25, 0 minus, now the 25 is cleared on this. So we're going to subtract, I'm going to multiply the 3 through. So you're going to have a 0, 9, 12, and then minus 1, 0, 0. Okay, like that. And then, so the components will be 25 minus 0 minus 1, so that's 24. Next component, 25 minus 9 is 16. Minus 0, so that's just 16. And then 0 minus 12 minus 0, so that's negative 12. And I got to say, I kind of want to divide that by 4. So instead of multiplying by 25, I'm going to multiply by 25 fourths. And then put a 1/4 out of all this. I've already run the 25 through. So I'll say times 1/4. So my final form will be 6 for negative 3. And I think there's a mistake. And we'll subtract the 25, 0, 0, like that. So then the first coordinate, I see 25 minus 0 minus 25, so that's just going to be a 0. Second coordinate, I'm going to have a 25 minus 0 minus 25, so I think, in a minute, 25 minus 9 minus 0, so that's 25 minus 9 is 16. And then third coordinate is going to be 0 minus 12 minus 0, so it's negative 12. And the only thing I would do to change this is that I had previously multiplied by a 25 to clear the denominator on one fraction. I'm going to multiply by 25 over 4. And so this second expression down here, I'll multiply by the 1/4. I did distribute the 25, but not the 1/4. Let's just do it in one last step. So this comes out to be 0 for negative 3, and that's it. Okay, now I forgot, I need to make these unit vectors. So just real quickly, I went ahead and did a little rearranging just to make some space. And then let's just take a second here and say the magnitude of W1 here is going to be the square root of 0 square plus 3 square plus 4 square. Of course, that's the square root of 25. Okay, so that's 5. Easy. The magnitude of W2, that's just a unit vector already. So the magnitude of W2 is already 1. So there's nothing to do to that one. This guy for W3, that looks pretty easy also. So this can be really similar to W1. So the magnitude of W3 is going to be the square root of 0 square plus 4 square plus -3 squared, like that. So that's, of course, the square root of 25 again, which is 5. So in the end, we were supposed to give unit vectors. So I think I'll call my unit vectors u1, u2, and u3. So for the unit vectors, which are our orthonormal set, I'm going to go ahead and say u1 is going to be w1 over the magnitude of w1, like that. So we're just doing that 0, 3, 4 and dividing it by 5. So you're going to get 0, 3/5. Make this a little bigger. 0, 3/5 and 4/5, and that's a unit vector. Okay, u2 is already set. U2, I'll just make w2. You know, you can say it's w2 over the magnitude of w2, but that's just 1. So there's not much to do there. So this will just be 0, 0, 1. I'm going to make a little space here. Okay, so that's just 0, 0, 1. And forgive me if I use angle brackets sometimes on my vectors. That's my Math 280 vectors coming out, just using different notations. And then U3, third unit vector will be W3 over the norm of W3, or magnitude if you like that. Okay, so W3 was 0, 4, -3, and the magnitude was 5. So we'll just do 0, 4/5 and -3/5. And so that one is an orthonormal set. They're perpendicular to each other and they're all unit vectors. They act like an IJK coordinate system, but they're different. Okay, so we've got number 45 here. The inner product of functions is what we're going to work on. So let's work on A first. So we have to do the inner product of f and g on the interval from 0 to 1. So that should be pretty easy. So we'll integrate 0, 1, f times g dx. So here that's going to be f times g. So that's going to be x times x to the third. So obviously that's x to the fourth, which is going to give you a 1/5 x to the fifth from 0 to 1. And I think that'll just be a fifth. Okay, so that's easy. Let's do B. The magnitude of G is the it's the square root of the inner product of G with itself. So this would be the square root of the integral from 0 to 1 of G times G. G is x to the third. So this is going to be x to the third times x to the third dx, like that. And so this would be the the square root of the integral of x to the sixth. So that'll be 1/7 x to the seventh from 0 to 1. So that'll just be, square root of 1/7, which is going to be 1 over the square root of 7, which I'll probably simplify eventually. Okay, C, they want the distance from F to G. So the distance from F to G is the norm of F minus G, okay, which is going to be the square root of the inner product of F minus G with F minus G, like that. So this would be the square root of the integral from 0 to 1. F minus G is just what? That's x minus x to the third. Like that. And that multiplies by itself, so it ends up getting squared, and I'll put the dx in there. Okay, and we're going to have to multiply that out. So get the square root from 0 to 1. And here goes. I'm going to write it in descending powers. So we're going to have an x to the 6th. Minus, let's see, the inner times the outer. That's going to be an x to the 4th. And there'll be negative 2 of them. Minus 2x to the 4th. And then just plus x squared. And that'll be dx. Like that. Easy enough. So we're going to get a 1/7 x to the 7th from 0 to 1 minus a 2/5 x to the 5th from 0 to 1 and plus 1/3 x to the 3rd from 0 to 1. And then the whole thing ends up inside a square root. So I'm going to move this over just a skosh. Okay, take square root of all that. Like that. So it's a little ugly, but not bad at this point. So we have to do 1/7 minus 2/5 plus 1/3. So shoot. Common denominator. So we're going to have to really work this thing. So you're going to do 3 times 5, which is 15 over something. And then with the 2, you're going to have to multiply it by 7 times 3, which is 21. So minus 42. And with the 1, you're going to have to do 7 times 5, which is 35. And 7 times 5 times 3 is 35 times 3 is 105. Okay. So 15 plus 35 is 50 minus 42, that's 8. So I think you're going to get the square root of 8 over 105. And, you know, you can do all kinds of stuff to this. Again, I think I'm going to leave the cleanup to you. But the top and bottom essentially is going to get multiplied by the square root of 105 on that one. Okay, and then on D, it's asking us to orthonormalize. Oh, so that reminds me. I didn't do the other one. That's okay, we'll go back to that. Okay, the orthonormal. First, we have to do Gram-Schmidt. So let's say W1 is going to be F, which is just going to be, what's the first one? X. Okay. And then I could just copy the formula from the other problem that we did. Where was that? Right here for W2. But I'll probably change the notation. So this is the Gram-Schmidt notation for the second vector. Okay, so I guess we could call we could have like a V1 and V2. So the X would be like V1 and the G would be V2. So technically the W1 would be V1. Okay, so I'll just call it V1 just for the sake of it. And then let me paste in the formula from the other for W2. And I'm just going to get rid of the barbs. I don't know why. I don't want barbs there. And then maybe I just remind you, the inner product notation is a little different in when we do a generalized context. So I'm going to use the standard inner product notation, which is the angle brackets, like that. And then just remembering that V2, I think, was the x to the third. Okay. Oops. X to the third. That. Okay. And then we would do x to the third minus this first inner product. So this would be the integral from 0 to 1 of V2 and W1. So V2 is the x to the third, and W1 is just x. That's going to be, I think we're going to get a fifth, and I feel like we did this one already. Yeah, that comes out as a fifth. So dx over, we're going to do the inner product of W1 with itself. So from 0 to 1, we're going to do x times x dx. And then this whole thing gets multiplied by W1, which is just x. Okay, I did this strange thing again where I put a subscript of a 3 on the x. It should be x to the third. And I apologize about that. I'm sorry. Okay. I think I can do most of this in my head. I am going to write x to the third, and it's going to be minus the numerator. That's an x to the fourth. You're going to just get a 1/5 on top. I already said that, I think. And then the denominator, you're going to get an x squared. Antiderivative is going to give a 1/3. And that'll be times x. Okay, and then I'll remind you also that you can multiply these by scalar. So, I would probably go with x to the third minus 3/5 x. Okay, and then I probably just multiply the whole thing by 5. Because the whole point is to make them perpendicular, but it doesn't matter how long they are, what their magnitude is. Okay, so in the end, we're going to get 5x to the third minus 3x. And that's going to be orthogonal to x up above. Okay, now they want us to make these unit vectors. So for units, I'm going to have to come down here, I guess. So the magnitude of W1 is going to be the square root of the inner product of W1 with itself. And W1 is just the x. So you're going to do the square root of the inner product, which is the integral from 0 to 1 of just x times x. And there'll be a dx. So in the end, I think you're going to get a 1/3 out of that. Okay, and we have to take the square root of that. So it's going to be 1 over the square root of 3. I feel like I've done that also. No, didn't. Okay, we have to do the magnitude of W2 now. So the magnitude, this will be harder, of W2 is the inner product of W2 with itself and the square root. Oops. Okay. Okay, so this will be an integral, square root of an integral from 0 to 1, and we're just going to multiply w2 times w2. So you're going to get that 5x to the third minus 3x. And that has to get squared because you're multiplying it by itself, like this. Okay. And this will be a little bit ugly. We're going to have to multiply this out. So integral 0 to 1. I guess we're going to have a 25x to the 6th. Right? And then you're going to have minus 30. X to the 4th. And plus 9x squared. Like that. Oh, it's horrible. And now we integrate. So this will be square root. I think I'm going to just do a lot of this in my head. So you're going to have 25x to the 7th over 7 from 0 to 1. So that's just going to be 25 over 7. The next one's going to be 30 over 5. X to the 5th from 0 to 1. So that's just going to be 30 over 5, which is 6. So it'll just be minus 6. And then the next one, you're going to have a 9 over 3 x to the 3rd from 0 to 1, which is just going to be 9 over 3. And so that's just plus 3. Okay. So 25, if we do, so it's 25 over 7. And then negative 6 and 3 is going to be minus 3, which is 21 over 7. So it'll be minus 21 over 7, which is the square root of 4/7, which is 2 over root 7. Okay. And then so the unit vectors would be W1 over the magnitude of W1. Okay, so W1 is just X. So this would be X over 1 over square root of 3. So that's just root 3x. Like that. And then the next one's going to be W2 over the norm or the magnitude of W2. Like that. So this would be, well, I'll just write root 7 over 2, and then we'll multiply by W2, which is 5x to the 3rd minus 3x. And I'm just going to leave it like that. That's fine. Okay, so let's do a quick number 47. This looks pretty easy here. So I don't think we need to go to matrices or anything here. We can just say x1 is negative x2 minus x3. There's nothing here to tell me what x2 and x3 are. So let's go ahead and say x2 is s, x3 is t. And so I think x1 will be minus s minus t. So my vector, let's just say x, which has the x1, x2, x3 components, will be negative s minus t. S and t, which we want to make into the span of 2 vectors. So the first vector will be any multiple of negative 1, 1, 0. And negative 1, 0, 1. Okay, so W is the span of these two vectors. Like that. But those are not orthogonal. You can check it real quick. When you dot them, you get 1. So we need to use Gram-Schmidt. So I'm going to call this first vector V1, and this one V2, and then W1 will just be V1. So that's going to be the -1, 1, 0. Okay. And then W2, we have to take V2 and subtract the W1 component of V2. So we're going to subtract out the inner product of V2 with W1 over W1 dotted with W1. And again, I'm just doing the Gram-Schmidt process here. So this formula is in your notes. It's like the third time I've used it in this review. Okay. So let's see what we can get here. So with V2, that was -101. Okay, and then minus, if you do V2 dotted with W1, I think you just get 1. And then if you dot W1 with itself, looks like you get 2. Okay, and then multiply this by W1, which would be -110, like that. And I think we'll multiply the whole thing by 2 to clear the fraction. Okay. So we're going to have -2 0, 2, and then it'll be minus -110. And just watch for the double negatives here. So -2 minus -1, -2 plus 1, so that's -1. And then 0 minus 1 is -1, and then 2 minus 0 is 2. And so these should be orthogonal. So let's just note that W1 dotted with W2 is -1 times -1, that's 1, plus 1 times -1, that's -1, plus 0 times 2, which is 0, so you get 0. And so that means that W1 is orthogonal to W2. Like that. So that's good. Now, were we supposed to make them orthonormal? It does say orthonormal here. So we're going to have to make them unit vectors. So let's let U1 be W1 over its magnitude. So W1 was the -110. And its magnitude is the square root of 2 if you check. So that's kind of ugly. And there's the first one. And then U2 is going to be W2 over the magnitude of W2. Okay, so W2 is -1, -1, 2. And then that'll be over the magnitude of that. So let's see, That'd be 1 plus 1 plus 4, 6. Just over the square root of 6. So I think we're going to have negative 1 over root 6, negative 1 over root 6. Oops. And then 2 over root 6. And I'll leave it to you guys to simplify all this. Okay, but technically you want to reduce or get the denominators rationalized. So these are orthonormal unit vectors. And they make a basis for this solution space, which was called W. And that's that. Okay, so now we're going to look at number 50 real quick here. Let me move that down just a skosh. Oh, that was not supposed to happen. All right, number 50. This is actually really easy. So if you have the norm of u plus v plus the norm of u minus v, you just need to remember that. Oh, and these are squared. So that's great because that's just the dot product of the vector with itself when you have the norm squared. So you would have u plus v dotted with u plus v, like that. And then plus u minus v dotted with u minus v. Okay, so that's equivalent. And the good news is, as you know, dot products distribute and they commute and they do all the things that you do with algebraic variables. So we can do this as u dot u plus 2u dot v plus v dot v plus u dot u minus 2 u dot v plus v dot v. And the u dot v's cancel because you see them on the left positive and on the right negative, like that. And if you notice, there's 2 u dot u's. So now you can just say there's 2 u dot u plus 2 v dot v, like that. And of course, that's 2 magnitude of u squared plus 2 magnitude of v squared. And we're done. Okay, so on 62, our job is to find the least squares regression line, which is just a line of best fit. It's you're trying to find a line that goes through the points when the points don't line up. So this ends up being a system of equations that has no solution, but we find the least square solution with it. So these points, we want them all to go through or to be contained in one line. So the equation of the line is y equals mx plus b. We would probably write this as mx plus b equals y, and then plug in all the points. So for the first point, you would do m times x, which is negative 2, plus b, which is equal to y, and y is 2. Then the second point, you're going to do mx, which is negative 1, plus b equals y, which is 1. Third point, mx, which is now 0, plus b is y, which is 1. And then the fourth point, mx, which now is 1, plus b equals y, which is 3. So that's 4 equations, and 2 unknowns. It's a very much over-determined system of equations. I would probably write it in vector form. So you'd have the coefficients of m, -2, -1, 0, 1. In the first column, coefficients of b are all 1. Okay, and that's all times m and b. Like that. Equals the vector of constants. These are all the y coordinates, which are 2, 1, 1, 3. Like that. Okay. So this is just the vector form of a system of equations. This is like ax equals b. Okay, so the b vector is the vector of constants. X is the vector of unknowns. A is the coefficient matrix. Okay, and the least squares solution is found very simply by multiplying by A transpose. So you left multiply by A transpose for the least squares solution. It's the weirdest thing ever. So that is, you would do A transpose A X equals A transpose B. So it's just the weirdest thing in vector algebra, that when a system of equations doesn't have a solution, you just left multiply by the transpose of the coefficient matrix, and that'll be a solvable system. So let's do it. Okay, so A transpose, you just switch rows and columns. So you're going to do, first row will be -2, -1, 0, 1. Okay, and then the second row is all the ones, like that. So there's A transpose. And then I'm just going to copy the A from what we wrote before. Paste it down here, like that. And then equals, I need A transpose again, so I'm going to copy my A transpose over, times the B vector, which I'm just copying. Okay, so that looks horrible, but it boils down to something super nice. So we'll just go ahead and you can note this is a 2x4 times a 4x2. So in the end, you're just going to get a 2x2, which is much more manageable, times the MB vector of unknowns. And again, a 2x4 times a 4x1, which will give a 2x1. Like that. So here we go. -2 times -2 is 4, 5, 6. So I think you get a 6 in the upper left. Okay. And now we're going to do -2, -3. So it's just a -2 here. And think you're going to get a -2 there and a 4 there. Okay. And on the left side, you have to do -2 times 2. That's -4 minus 1, -5 plus 0 plus 3. I think it's -2 here. And then 2 plus 1 plus 1 plus 3 is 7, I think. Okay, so that's your simplified system of equations, which you can now solve, and you can solve it any way you like. I'm going to go ahead and go this route. like that. So I think I'm going to switch row one and two. It just seems easier. So we'll get a -2, 4, 7 there. And then the 6, -2, -2 here. Okay. And now we'll do 3 row 1 plus row 2 into row 2. Okay, and I'll do that down here. So first row doesn't change, -2, 4, 7. But you get -6 and 6 is 0. 4 times 3 is 12 plus 2, that's going to be a 10. And 7 times 3 is 21 minus 2 is 19. Ugh. Okay. I guess I've seen worse. It's ugly. So I guess we'll divide row 2 by 10. So 1/10 row 2 into row 2. So we're getting -2, 4, 7, 0, 1. And you say 19 over 10, or you could say 1.9 if you like. I think it's okay to use decimal on this one since I'm not rounding at all. Okay, so now I need to do -4 row 2 plus row 1. And we'll stuff that into row 1. Okay, so we're going to do 0 and -2 is -2. And then do -4 and 4, that gives us a 0. And then -4 times 1.9 on my calculator plus 7 comes out to be -0.6. Second row doesn't change, 0, 1, 1.9. Obviously, we need to divide by -2 on the last step. So we're going to do -1/2 row 1 into row 1. Okay, so then the last thing is we get a 1, 0. So I think we're going to get a 0.3 and a 0, 1, and 1.9. Like that. Okay. And so from this, you can say that M, the first unknown, is 0.3 and B is 1.9. And so the line of best fit is Y equals MX plus B. So that would be Y equals 0.3X plus 1.9. Okay, now they're asking us to graph this, so and the points. So I'm going to go ahead and put in some graph paper real quick. Okay, so let me put a coordinate system in. That didn't work. I'll try again. Okay, so I'll go to there, I guess. What are my points? I have to do nothing bigger than 3, but my x coordinates go back to -2. So let's go like this. Okay, so my first point is -2, 2. I think I can do that here. Second point is -1, 1. Like that. Third point is 0, 1. Like that. And the fourth point is 1, 3. 1, 3, like that. That really looks horrible. And somehow I'm supposed to find a line that goes through these. I think that's sort of almost inappropriate. But That's fine. Oops, 1.9 on here. There we go. All right, so I have y-intercept of 1.9. I think I can pull that off. Put a little x right there. 1.9, this is fine. And then let's see, if x is 2, I can see my y-coordinate would be 0.3 times 2, which is 0.6, plus 1.9, which is 2.5. So I would have another point right there. And those together would make my line of best fit. So I'm going to go ahead and put that in here. I'm going to make it a little too long. And then I'll move it up a bit. And again, this is supposed to be the closest line to contain these 4 points. And as I've said, that's an impossible problem, but that's the closest we're going to get to a solution. Okay, so I'll just do a little labeling, and I think that's good enough. Okay, so that's number 62, and I think that's it for the chapter 5 material. So I'm going to pause and we'll go to the next chapter in a bit. Okay, so now I'm on the chapter 6 problems. This first one just asks you, basically you're expressing this linear transformation in matrix notation. So I like to write it this way. And if you're just careful, you can just see the matrix. So there's an x1 plus an x2 in the first coordinate. Second coordinate is just a mistake. Okay, so then we would put a 2 here, and then a negative x1 plus x3. This is not a linear transformation. So we don't have to define the standard matrix. And so this is a shame, because I wanted to give you one where you would have to find the standard matrix. So this is not linear, since t of the 0 vector is not going to map to 0. That's t of 0, 0, 0, basically. And if you look at it, you're going to get 0, 2, 0. All linear transformations have to map 0 to 0. So that is to say that if t is linear, then t of 0 must be 0. It never moves the origin, is what that says. Okay, so this one's not a linear transformation, and we don't have to find the standard matrix because of that. And that's all you can do with number 15. Okay, so this is number 19. This one's asking if t maps 2, 0 to 1, 1 and 0, 3 to 3, 3, what's t of 1, 1? So what you want to do on a problem like this is note that 1, 1 needs to be expressed in terms of the vectors that they're giving me information of. So if you think of it as it's a half of 2, 0 plus a third of 0, 3. You just look at that for a second and make sure you see that. So that's what 1, 1 looks like. And the reason why I do that is because I know that 2, 0 maps a certain way and 0, 3 maps a certain way. So when I do t of 1, 1, this would be t of a half of 2, 0 plus a third of 0, 3. And the way linear transformations work is that they sort of distribute. So you can say this is a half t of 2, 0 plus a third t of 0, 3. And see, these we know all about. So this is a half. T of 2, 0 is 1, 1. And a third, t of 0, 3 is 3, 3. So I think we're getting a half plus 1, 1, which I guess is 3 halves, 3 halves, like that. Now they want t of 0, 1, which is almost too easy. T of 0, 1 is t of a third times 0, 3. And we know about 0, 3 up above. So this is 1/3 t of 0, 3, which is 1/3, and t of 0, 3 is 3, 3. So this is just going to be 1, 1. Okay, so this is number 23. So we have to figure out where to and from, where does this t map? And so Rn to Rm, we have to figure out the n and the m, I guess. T of v is a v. A is a 2 by 3. So v would have to be a 3 by 1. And this is equal to a 2 by 1 vector, which means that t, let's just say, so t maps R3 to R2. Because it takes an input of a 3 by 1 and it outputs a 2 by 1. Okay, so that's part A. Then B wants the image of V. So V is 611. So that's easy. So T of this 611 vector would be A. So 0, 1, 2, negative 2, 0, 0 times the 611. And as we know, this is going to be a 2 by 1. So we'll do 0 plus 1 plus 2. I think that's a 3. And then negative 12 plus 0 plus 0. So it's negative 12. Okay, so that's the image of 611. Doesn't look like a negative 12. I'm going to have to make that minus sign look a little better. So 3, negative 12 is the what they call the image of V, which was the 611 vector. Okay, and then they want the pre-image of W. Okay, so that means we have to figure out what maps to W. So T of V, let's just say is T of a vector that we'll call X, Y, Z. Okay, so this would be A, which is 0, 1, 2, negative 2, 0, 0, and that's times X, Y, Z. So XYZ will be the pre-image of 3, 5. Okay. And so if you work this through, the first equation, just multiply that matrix out and you get y plus 2z first, and then negative 2x in the second row, like that. So this has to be equal to 3, 5. Like that. So x is going to have to be negative 5 halves, and then there's going to be a whole bunch of solutions. So x is going to be negative 5 over 2. And then we have y plus 2z is 3. So maybe you could say that y is 3 minus 2z. But z can just be t. So y would be 3 minus 2t. So you would have to, if you want to write this as a vector, you would say that v is the xyz. Okay. Which would have to be negative 5 halves, 3, 0, plus t times 0, negative 2, 1. Okay, so any vector in this form maps to 3, 5. Which means you could pick any value for t. Put it in, and it would work just fine. So should I prove that to you? So for example, let's say t is 1. So if t is 1, then v will be negative 5 halves. 3 minus 2 is going to be a 1. And then 0 plus 1 is 1. Okay. And then if you do t of v, okay, this would be a times v. So a is way up there. I'm going to just grab it. A times v. And I think I have to readjust a little here. Like that. And I hope this works. So you get 0 plus 1 plus 2, that's 3. And then negative 5 plus 0 plus 0. Positive 5 plus 0 to 0, 3, 5. Okay, so it mapped to 3, 5. Okay, so that's going to be a line in R3. All the vectors that satisfy this description form a line in R3. Okay. Okay, so 27 is just like 23, which I just did. Actually, 27 is easier. So I'm just going to walk you or talk you through this one. T of v is supposed to be a times v. Okay, a here is a 3 by 2 matrix. V is a 2 by 1. At least it's from R2, so it'll be expressed as a 2 by 1. And when you multiply a 3 by 2 times a 2 by 1, you're going to get a 3 by 1. So the input is 2-dimensional. So from R2, the output is three-dimensional. This goes to R3. So T maps R2 to R3. T of V is A times V. A is this. The V they want us to use is 2, 2, and we're trying to find the image of 2, 2. So you just multiply this, and you get 8, 10, 4. And so 8, 10, 4 is the image of 2, 2. Okay, now we need the pre-image of 4, negative 5, 0. That's the next question here. So we're trying to find a vector, call it xy, so that A times xy will be 4, negative 5, 0. So when you do A times xy, you get 4x, 5y, x plus y. So clearly 4x is 4, which means x is 1. 5y is negative 5, which means y is negative 1. Thankfully, x plus y, as it says, it needs to be 0. So x has got to be 1, y is negative 1. So t of 1, negative 1 is going to be the 4, negative 5, 0. So 1, negative 1 is the pre-image of 4, negative 5, 0. Okay, so this one's just, number 29 is just a rotation problem. So if we recall that we've covered this before, t of, let's say, xy has got to be cos theta, negative sine theta, cos theta times xy. Okay, so this rotates by an angle of theta about the origin. Counterclockwise. Okay, now they've given us a little triangle. They just want us to rotate this. This would be super easy. Here, we got to do 90 degrees. So our theta is 90 degrees. Okay. And we'll just show the work on this. T of xy. So cosine of 90 will be 0. Negative sine 90 will be negative 1. Sine 90 is 1. Cos 90 is 0. So there's your matrix. And that's a rotation matrix. 90-degree rotation. Super easy. So when we do t of the first point, 3,5. We're going to get 0 plus negative 5, and then 3 plus 0, so 3. Next point is t of 5, 3. Same matrix. And I'm guessing, let's see, 0 plus negative 1 times 3 is negative 3, and then 5 plus 0, like that. And then the last point, t of 3, 0. So here we're going to get 0 plus 0 is 0, and 3 plus 0 is 3. Okay. Now I'm going to get some graph paper going here. They want us to graph both triangles. And looks like I have to get some x coordinates of negative 5 and negative 3. So I think we'll just have everything go from negative 5 to 5. Hope that's going to work. Let's see, 5, 4, 3, 2, 1, 0. See if I get this right. Okay, so 1, 2, 3, 4, 5. That's okay. Okay, and so we got 3, 5, 5, 3, and the third point is 3, 0. So I'll put that right. Oops, hang on. 3 zeros right here. Okay, so these are sort of the original image. I'm going to try and draw a little polygon through these. Let's see if this works out. That's pretty good. That's fine. Okay, so that's sort of the pre-image of the image that I'm about to do. The outputs, let me switch colors here. So the outputs were -5, 1, 2, 3, 4, 5, and then up 3. So there's this point. There's a -3, 5 up here. Like that. And then, of course, there's a 0, 3. So 0, 1, 2, 3 there. Like that. And so these are the same triangle, but rotated 90 degrees. That did not work. Let me try it again. I'm trying to make my polygon now. Okay, I'm gonna try again. I don't know what my problem is, but hey, snap, snap, and snap right there. Okay, so pre-image and image. Okay, and that's a 90-degree rotation. So you can sort of see the rotation. Maybe if I put an angle on here. So let me draw an arc like this. That's our 90 degrees. About the origin. Like that. So that's obviously the kind of stuff we do in computer graphics all the time. Okay, so now we're going to do number 33 here. We want to see what the kernel is of this linear operator. I think I want to go ahead and do the standard matrix for it just so you guys can practice doing that. So standard matrix, you just stack it up like this. You start with T of X, Y, Z. And then sort it this way. So you've got the first coordinate is going to be X, second coordinate is Y, third coordinate is Z plus 3Y. So you put it so that the X's are lined up and the Y's and the Z's. So your X would just be sort of alone. And then the Y is going to be sort of alone. And then right below the Y, do a 3Y plus a Z. Like that. Okay, and that'll look like a 3 by 3 matrix. You could say X plus, X plus 0Y plus 0Z, you know? And 0x plus y plus 0z and 0x plus 3y plus z. And the point is you can see this is going to be 1, 0, 0, 0, 1, 0, and 0, 3, 1 times x by z. Like that. And if we're trying to find the kernel, then we would just set this to 0, 0, 0. And see what maps there. So, I mean, this thing is almost done. As a matter of fact, the kernel is just going to be the 0 vector. So if you put this in as an augmented matrix, like that, then you can do negative 3 row 2 plus row 3 to wrap this up. So in the end, you just end up with sort of an identity matrix with a augment on the right, like that. So this tells you that x equals 0, y equals 0, and z equals 0. So if basically if t of v is 0, then our vector v has to be this solution, the xyz vector, which is 0, 0, 0. Okay. And the range is basically the dimension of the column space. The dimension of the column space is going to be 3-dimensional because the dimension of the kernel plus the range has to be 3. Okay, so you could say here that the kernel of t is just the 0 vector. Okay, so the dimension of the kernel of t is the nullity of t, and the only, again, the 0 vector has no dimension. I guess to say it doesn't have no dimension, it has 0 dimension. So the nullity of the transformation is 0 because the 0 vector has no length or width. It is 0-dimensional. It's a point. Okay. So it's 0-dimensional. And then, you know, as far as the range, you may as well note that okay, and so just keep in mind, this is the sometimes called the rank nullity theorem, but it's theorem 6.5. This is an important one. It just says that the rank of the transformation plus the nullity of the transformation is equal to the dimension of the space that you're mapping in, the space you're mapping from. So this is the dimension of this. I'll just call this the dimension of V, where T is mapping V into W, like that. Okay, and just as also as another reminder, the rank of T is the dimension of the range of T. And I already mentioned the nullity is the dimension of the kernel of T. And the dimension of V, this is N, is what they call this in the theorem, it's the dimension, in this case, of R3, because we're mapping from R3 into R3 here. So N is 3. So what I'm trying to get at is I've determined that the dimension of the kernel is 0 here, and that N is the dimension of R3. Okay, so N is 3, and so the rank of the transformation plus 0 is 3. So that is to say the rank of the transformation is 3, which means the dimension of the range of T is 3. That's the rank of T. So this is 3-dimensional. If it's three-dimensional, then it has to be all of R3. So the question is asking the range of T here. So if it's three-dimensional and it's in R3, then the range has to be all of R3. Okay, so I want to look at number 37. This was originally number 35, which was kind of boring, and I wanted it to have a non-trivial kernel. Just real quickly, on 37, this one has a non-trivial kernel, so that's why I changed the problem. T of v is a times v. For the kernel, we need T of v, which is a times v, equal to 0. So my v is going to be like an xyz vector. And so if I do a times that, I'll have a 2, 1, 3, 1, 1, 0, 0, 1, negative 3 times xyz equals all zeros, like that. So if I want to solve this using an augmented matrix, I would do this. And row reduce. I'm going to go ahead and just give you the result of this. So if I apply the row ops to this, we end up with this result. 1, 0, 3, 0, 0, 1, negative 3, 0, which is that third row down there, and then all zeros. Like that. And so we can see that z can be t. Y is 3z, so that'll be 3t. And x is negative 3z, so that'll be negative 3t. So our vector v, which is xyz, has to be t, oops, has to be equal to t times negative 3, 3, 1. And any vector of that form will map to 0. Okay, so the kernel of our transform is just the span of this one vector, negative 3, 3, 1. Okay, so that's A. Now B, we want the nullity. That's easy. So the nullity of T is the dimension of the kernel of T. And the kernel is spanned by one vector, so this is one dimensional. Okay, C, I believe we want the range of T. So we can just remind ourselves that T of V is A times V, which, as you know, A is this vector or this matrix up above. I'm just going to copy it down. So my V is this XYZ vector, like that. And then just as a reminder, you can write this as 2, 1, 0 times x, because the 2, the 1, and the 0 all get multiplied by x when you do this matrix multiplication. Those are the x coefficients, and so this is one way of writing all the x coefficients together. And then the y coefficients are all 1, 1, and 0. So we'll put a y there, and then the z coefficients are the 3, 0, and -3. Okay, so which is another way of saying that these form a basis for the column space. So the range of T is the column space of A. Okay, you're just looking at the possible outputs of T, and it's just linear combinations of these columns. And so that is the definition of the column space. And so we just need basically a basis for the column space. And so the basis for the column space can be found by row reducing A transpose. And that way you're manipulating, if you do A transpose, as you do row operations on A transpose, you're actually simplifying the columns of A. So A transpose looks like this. And I'm just taking the columns and making them into rows. Oops, 2, 1, 3. I think I have a mistake. No, I guess we're okay. 2, 1, 0, 1, 1, 1. Okay, I see my mistake. That should be a 1, 1, 1 here. And then a 3, 0, -3. And then we're going to do row ops. So the row ops are actually working with the columns of A, but these are the rows of A transpose. And what do we get with that? Okay, so what that becomes is 1, 0, -1, 0, 1, 2, and then the third row zeroes out, which means this is two-dimensional. So the basis for the column space of A, which is the range of T, is just these the row vectors, which I will turn into column vectors again. So we'll do 1, 0, -1, and 0, 1, 2. Those will span the column space. Okay, and now in question D, I think they're going to ask for the rank. So the rank of T is the dimension of the range of T. Of course, that's the dimension of the column space, which is the same thing, and it's two-dimensional. Okay, and so note, we say that the nullity of T plus the rank of T is equal to the dimension of the vector space that you're mapping from. So the nullity was one-dimensional, the rank was two-dimensional, and V is R3, so this is going to be three-dimensional. Okay. Okay. Because you're mapping, I should say T is mapping from R3 into R3, just to remind you. So that's B. This is W. Okay. So that's good for that. Okay, now number 51, I hate to say it, but it's almost too easy. But I'm going to set this up as if it wasn't easy. So first of all, to express this linear transformation as a matrix transformation, T of xy is x negative y, like that. Okay. And I want to write this as x plus 0y and 0x minus 1y. And that allows me to break this into a matrix multiplication. So you'd have 1, 0, 0, negative 1 times xy. Okay, so this is A here, and this is my V vector. Okay, and so we just have to find the inverse transformation. So T of V is AV. And then T inverse of V we talked about is just the inverse matrix A inverse times V. So A inverse should be pretty easy. Like I said, it's almost too easy, but if we do A and we attach I with an augmented matrix, you'll get 1, 0, 0, negative 1. And then put the 1, 0, 0, 1 there. And then, of course, we're going to do negative 1 times row 2 and put that into row 2. So that'll give 1, 0, 1, 0, 0, 1, 0, negative 1. So that tells you that A inverse is 1, 0, 0, negative 1. Okay, so when I say it's too easy, I just mean that that was a bit trivial trying to find A inverse. So I probably make you work a little harder. I don't know. It's just a function of how much time and how many problems are on the test. If the test is getting long, then maybe it makes sense to put easy problems in like this. Just kind of testing concepts, but computations are a little light, but now you can just say T inverse of V is A inverse of V, or if you like, you could say T inverse of X, Y is going to be 1, 0, 0, negative 1 times XY. This is actually the same transformation you started with. So you can see this is X negative Y, and you multiply that out. And you can see that's the same transfer. So it's interesting to note T inverse is T on this example. That would normally not happen. Okay, so just an interesting kind of a thing that happens. And I think that thing reflects, it takes the y coordinate and makes it negative. So it's just reflecting it through the x-axis. And if you reflect a point through the x-axis, you get a mirror image down there. And if you reflect it back, it just comes back to the original location. And that's why if you apply the transform twice, it undoes itself, which means it is its own inverse. Okay. So that's why T inverse is equal to T on this one. Okay, so that's 51. Okay, so let's do this number 53. We have to do a whole bunch of stuff. They give us a matrix, and I guess we should add that T of V is A times V. And because this is a 2 by 2 matrix, we should say maybe that T maps from R2 into R2. Okay. And there's a couple of interesting theorems, and I think we almost should take the second one first. So let me put this one up first. Okay, and so what it says is that if a linear transformation has a kernel that's 0, then it's 1-to-1. Okay, if it's 1-to-1, that's true if and only if the kernel is 0. So let's just first determine that. So the kernel of T is a set of vectors V such that T of V is 0. Okay, so let's go ahead and figure that out. So T of V is going to be AV. A is this 6, 0, 0, -1 times V. We'll call V just XY. Like that. So this is super easy. It's 6x and -y. And this has to be equal to 0, 0. That's our 0 vector. If we want to find the kernel, and then of course 6x has to be 0 and -y has to be 0, which means of course that x is 0 and y is 0. So our vector v is the 0 vector. So the only vector that maps to 0 is 0. So that tells you that the kernel is the 0 vector. So the kernel of T is just one vector, 0. Okay, so that fact tells you that T is 1-to-1. Okay, so T is 1-to-1. And I'll just say by theorem 6.6. Okay. And then because T maps R2 into R2 that have the same dimension, so since T maps R2 into R2, the domain and the range have the same dimension. I don't want to call it the range because that's something else. So both have the same dimension. Then theorem 6.8 says that if it maps from V into W and both V and W have the same dimension, N, then T is 1-to-1 if and only if T is onto. So, by theorem 6.8, T is onto. So we can say that. Okay, and let's see if we've answered everything here. It says determine whether the transformation is one-to-one onto an invertible. And well, I guess we better grab another theorem here. So let me pause for a second while I grab the other one. Okay, so then I went ahead and grabbed theorem 612, which says basically the following are equivalent: that a transformation is invertible, okay, that it's an isomorphism, or that its matrix is invertible. These are all the same thing. So just to remind you of an isomorphism, it says that T is 1 to 1 and onto. Okay, so if it's 1 to 1 and onto, then it's an isomorphism. And if it's an isomorphism, then it's invertible. That's basically our argument here. We've got 1 to 1 and onto above. So I would add by theorem 612, T is invertible. Okay, so the questions were to determine if the matrix is, the transformation is 1 to 1. That was covered here. Onto was covered here. And invertible is covered here. So that's done. And I think that's the review. I'll post these solutions on Canvas along with the video. All right, see you guys.